Good afternoon or good morning, everyone. I guess we'll get started now. Welcome to the webinar on the SwiftMote-Electrochemical sensing platform that CMC has developed in collaboration with researchers at the University of Sherbrooke. I'm Hugh Pollitt-Smith. I'm the team lead for IoT and Edge AI, and I'm joined in the room by my colleagues James Miller and Olive Zhao, who also work in the Embedded Systems group here. In terms of the agenda, I'll give a brief introduction to Fabric, which is a new initiative managed by CMC, and then I'll turn it over to James and Olive to discuss the hardware and software aspects of the platform and show a brief demo. So Fabric is a 5-year, $223 million project that was launched in July. It's managed by CMC Microsystems, and the intent is to lower barriers faced by Canadian companies to develop and commercialize semiconductor manufacturing processes and to bring IoT products and services based on those semiconductors to market, as well as to build a national semiconductor ecosystem in Canada and foster collaborations between SMEs and universities and government. And it's financed from Government of Canada, ISED. In terms of how Fabric operates, there are two key aspects. One aspect is the Fabric challenge calls, and these are periodic calls for projects from SMEs and researchers to either develop fabrication processes in Canada or to bring IoT products to market. And these calls responses are evaluated, and then projects can be funded up to 50% for small and medium-sized companies and 100% for academics. And then in addition to the calls, there's the innovation platform, which is an extension of the services that CMC has provided for over 40 years. So that includes the design, access to CAD tools, and prototype manufacturing and fabrication in a variety of technologies, training, and then access to quantum computing and quantum computing resources. And the last aspect is community leave-behind resources. And these are IP that are developed either through the challenges or by CMC or by the research community, and that are available to the ecosystem. So the SwiftMote platform is one example of those types of leave-behind resources that will be available through Fabric. Fabric is accessed through membership. You can become a member of Fabric at no cost. Just go to the Fabric member portal. You can register there. And this provides access to the registry, to see other members, or the IP registry where the leave-behind resources will be listed. There's training and events available, the IP repository where the leave-behind resources will be housed or available for download or other access, and other documents. And to become a Fabric member, again, there's no cost for membership. Academic subscribers are, I think, automatically members, although they have to register, and they get access to the same sorts of services they had from CMC previously. So the best source of information on Fabric is the new website, fabricinnovation.ca, or there's also an email address for any questions on becoming a member or the resources that are available through Fabric. And without further ado, I'll turn it over to James.
Okay, thank you, Hugh. So for the next portion of the presentation, I'll give a brief introduction to the application, how it works, and the hardware that makes it happen. This will be followed by a presentation on the software and a demo by Olive Zhao. So this picture shows a hospitalized individual lying in bed with their medication being monitored. And the medication may have a narrow acceptable range to work properly. That is, just enough to be efficacious, but not too much or too little to cause harm. So one needs to know the concentration at any given time and know when to top up the medicine. It would also be useful in some cases to have the patient go about their day a little more freely than just being left in bed. This project is a collaboration between the University of Sherbrooke, biomedical, and CMC Microsystems. So here's system overview of what we'll be talking about. And basically on the left-hand side, we have an electrochemical cell. This could represent or even be the bloodstream of the patient with a target medicine to monitor. In that electrochemical cell, we have 3 probes, one of which is functionalized by the University of Sherbrooke to detect only the target medicine that we are interested in. In the middle is what we call SwiftMote-Electrochemical, that wireless sensor board there. This is a Bluetooth interrogation system and the focus of this presentation. Data acquired by SwiftMote is then transferred to the PC using Bluetooth. So here's a block diagram breaking things down, showing you what's handled by the 2 main chips, the wireless control on the left and a device called a potentiostat on the right with analog inputs. In order to interrogate the system, our electrochemical cell, we generate a square wave waveform from SwiftMote. So this causes a redox reaction or oxidation and reduction reaction to take place in the electrochemical cell. The pulsed waveforms offset increases in voltage over time, and we measure the forward current at the end of the crest, so that's the IF in the diagram there, and the backward current at the base of the waveform, that's IB in the diagram. The difference between these 2 measurements gives us another curve that tells us something about the target medicine. So after plotting the difference in current versus the applied potential, we get this curve with a peak where we find the maximum oxidation and reduction taking place. The difference between the peak and the baseline there at the bottom, where it's more horizontal, tells us about the concentration of the target medicine. So this peak minus the baseline is proportional to the target concentration that we're trying to detect. The peak will decrease as the target medicine decreases or as it's metabolized in the body, but it should not shift horizontally on the graph. So to do this, we use what's called a potentiostat, and basically voltage is output on what's called the counter electrode or the CE pin, and it's monitored at the reference pin or RE. At the working electrode, labeled as WE, we have the functionalized probe to detect the target medicine where the redox reaction is taking place. The system maintains a constant potential between WE and RE while measuring the current flow from the redox reaction on WE. And this is how it's in general implemented at a high level. So we can fundamentally implement it with a couple of operational amplifiers, where on the left there, Vn is the voltage we want to set at the positive input of the operational amplifier, and the negative input is our feedback from the reference electrode. The current between CE and WE flows in proportion to the redox reaction at WE. The current then flows through the feedback resistor of the current follower amplifier, also known as the transimpedance amplifier, and that voltage drop across the feedback resistor, RF or RTIA it's sometimes called, is your input to the analog to digital converter downstream. So that voltage is proportional to the current that you're measuring. To do this, we selected the analog devices, 5941 potentiostat, and it has a few sections to it. A low bandwidth section, which is good up to about 200 hertz operation, and a high bandwidth section good to 800 kilosamples per second or 1.6 megasamples per second operation, depending upon how it's configured. These feed into further post-processing blocks, including gain, filtering, time domain averaging, or Fourier transforms on the data if so desired. The output is then sent out the SPI bus to the Blue Energy Bluetooth processor. The yellow part's highlighted as that is the section that we've been using for our experiments. This is just a deeper dive into that yellow section, the low bandwidth loop out of the datasheet. As you can see on the top right, there's the LP DAC. We use the 12-bit DAC for fine-grained control of our waveform that goes into the control amplifier and comes out the CE pin there on the left. And we use the 6-bit portion of the DAC to set a virtual ground. So that blue line heading down to the LPTIA, that's your current follower mentioned in the other slides. So we set a virtual ground somewhere in the mid operating point of this battery operated device. So if our range is say 0.2 to 2.4 volts that we can output on CE, then maybe the midpoint is say 1 volt, and then you can go above and below that. The SE port, or sensing electrode, is the same as the working electrode, or WE, and the user has the option of changing various input and feedback resistors on the chip to fine-tune their circuit or add filtering options before the analog signal goes into the ADC mux. So that's it for the current hardware, and I'll hand it over to Olive Zhao to talk about the software.
Thanks, James. Okay, so I'm going to take a few minutes to give a brief introduction on the software component of the platform through a demo application. So this application primarily implements two functions: data acquisition and data transmission. It has a client-server structure as shown in the picture, with communication handled by a Bluetooth Low Energy protocol. The client is a Python program running on PC that is responsible for sending commands and configurations to the mode. The mode means the SwiftMote-EC. The SwiftMote-EC. I will use a BLE, refer to Bluetooth Low Energy, in the next couple of slides, and I will refer SwiftMote-EC platform as mode. So the client also responsible for reading data from the server. So the server, on the other hand, is a C program running on that mode. Is responsible for accepting user configurations and commands, generating sensor data, notifying the client whenever the sensor data is available to read. The communication between the client and the server begins with the connection, BLE connection establishment. Once connected, the client would register itself to the server to indicate which content on the server it's interested in. In our case, the data would be, the content would be sensor data, or we say timegram data generated by the AD5941 potential stat. At the same time, with the connection, the client can send commands and configuration to the server. On the server side, whenever new data is available, the server would notify the client to read. So here's a control flow on both the client and the server side. The main body of the program on both client and server runs within an infinite loop to maintain continuous operation. On the client side, the process began with BLE connection establishment. Then once the connection is there, it sends user configurations and commands to the server. So before reading data from the server, the client first would check the connection status. If the connection is alive, it proceeds with retrieving data. Otherwise, it re-establishes the connection and then resume reading data. So once the data is received, it's processed and saved to a file. On the server side, the process starts with initializing the system, establishing BLE connection. Upon receiving user configuration and commands, they are passed to AD5941. The AD5941 would generate the botanogram according to the configuration and the commands. So after the botanogram data is available, the server informs the client to retrieve the data. Similar to the client, the server always checks the connection status before communicate with the client. If the connection is lost, it would re-establish and before proceed with data transmission. So here's a list of tools and devices used during the software development. A community version PyCharm, which is free, is used to develop the client program. ARM Kyle Microvision Edition was used for the software development on the server side. We host the code and documents on GitLab and GitHub. And there's a few libraries involved in the application. Python modules and the Bleak library are used for the client application program development. And the Bleak library is Bluetooth low energy implementation in Python. And ST-BlueNRG-LPDK and the AD5941 library are used for the server development. So ST-BlueNRG-LPDK is ST BLE stack and driver for the BlueNRG chip. AD5941 library is the driver for the AD5941, as well as algorithms implemented for data processing. So there are a few other hardware devices and software tools that used to support the development. So for example, the ST Railroad and analog devices Railroad were used to prototype the system functions at the beginning of the project. A Sega debugger unit was used for programming the board as well as debugging the application. Digilent analog device Discovery 3 is used for as a power supply to supply power to the moat, as well as used as a scope to monitor the output from the AD5941. So Nordic Power Profiler Kit was used to check the power consumption of the system. Wireshark is a free tool used to capture BLE data packets over the air to identifying BLE-related issues. There's a few other accessories like resistors, breadboard, battery, jumper wires are also needed. So the SwiftMote-EC platform is designed for portable, low-power, battery-operated applications, which makes power consumption a crucial concern. There are a few approaches available to reduce power consumption, including preventing leakage current by properly configuring all the I/O pins, implementing the BlueNRG-LP power saving features that allow us to put system in sleep as much as possible, and minimizing the duration of power-intensive operations by adjusting the parameters of Bluetooth communication and by adjusting the parameter configured to AD5941 during data acquisition. So this slide presents the result of two tests. The first test compares the platform's power consumption with and without the implementation of the power saving features. But the second test evaluates battery life. In the power consumption test, we measure the power consumed to generate and transmit 1 watt-gram. For this test, the motor was connected to a dummy sensor network with Bluetooth connection interval set to 5 seconds, and the maximum transmission unit size set to 247 bytes, and the transmission power level set to 15 dBm. On the 805941 side, so we set the square wave frequency to 80 Hz, and it generates a total of 300 data points per watt-gram. So as shown in the table, you can see prior to implementing the Bluetooth Blue NRG-LP sleep mode and have the I/O pins properly configured to prevent the current leakage, the power consumption for generating and transmitting 1 watt-gram was about 6.36 milliampere. So after we have the Blue NRG-LP power saving feature implemented that puts the system into sleep every 5 seconds, and we also properly configured all the I/O pins, the power consumption on generating and transmitting 1 watt-gram drops to 1.49 milliampere. So this is a reduction of about 78%. The battery life test was conducted by our client, the Sherbrooke University team. So their application requires a runtime of 6 hours. So the test setup include the mote connect to an electrochemical cell, contains the PBS, and powered by a LiPo battery. So the battery is slightly larger than a quarter, as you can see in the picture on the right side. Its weight about 5.57 grams. During the test, the square wave frequency was set to 80 Hz, and 700 data points were generated for each watt-gram. Data was transmitted from server to the client every 20 seconds. The test continued for 7 hours and then stopped by the client, at which point the back voltage had dropped about 100 to 200 millivolts. So that's a range because during the test, the client didn't record the exact voltage drop, but they sure that this range should be accurate. And then next, I'm going to do a demo of the application. As shown in this slide, the picture on the left side shows the setup of the demo on my desk. So the picture on the right side provides a zoom-in view of how the LiPo battery connects to the mote through a voltage regulator, and the mote is connected to a dummy sensor network that is composed of resistors and capacitors. And then I'm going to have to play here. I'm going to play this demo video. So as you can see, once the mote is powered on, and launch the client application on the PC, and then click the connect button to initiate a BLE connection. And then once connected, continue click on continuous run button to command the mote to continuously generate watt-grams. In this video, the blue NRG-LP is configured to transmit data every 5 seconds with a square wave frequency set to 80 Hz, generating 120 data points per watt-gram. This video lasts about 60 seconds, taking about 16 seconds to initialize the system and establish the BLE connection. In the remaining 44 seconds, about 8 watt-grams were generated and submitted. I think that's it. Yeah, that's just the 1 minute demo. This would be wrap up my part of the presentation.
Okay. Thank you, Olive. Okay, so how to obtain SwiftMote-Electrochemical. SwiftMote-Electrochemical is completely open source. All project files developed by CMC are available in source form. It's going to be, however, some separately downloadable ST development kit files, but everything that CMC worked on is completely open source. And we use KiCad for the hardware as well. So that's a free PCB design tool that you can use. Version 1 is available on GitHub for everyone to see and download. Subsequent versions will be available on GitLab for Fabric members. If you wish to obtain a pre-built version, then just get in touch with us by email. If you are interested in modifying SwiftMote, so there's, as we mentioned, the project source files are open source and you can get going with those. Or if you want to have a manufactured version of it, then there are a couple of expansion ports on it. One coming off the Blue Energy Bluetooth processor chip with your I2C and some ADCs and GPIOs, or off the 805941 potentiostat, there are additional analog input ports. We're also working on a new system, and looks similar to what you see in the picture there. It will include some additional calibration resistors. Instead of the 50 mil headers, we'll have 100 mil headers, so it's easier for you to use jumper wires and gain access to things. More indicator LEDs, and the ability to plug the system into a prototyping board to add your own hardware to it a little more easily as well. Whoops. We're also interested in anything else that you may need that we could add to the platform. We're currently using the low bandwidth loop. Maybe you have some higher speed sampling requirements, or perhaps you need to sense pH. There's just, a list of potential options that could be added to it there. Let us know at the end of this presentation, or email us lab@cmc.ca. At this point, I'd like to thank you all for attending.